All right, so the first thing that I want to tell you, I have two in generals to pass along. The first in general is that like the work that we did with rotation and with work in energy and springs, I'm not going to give you like a written test over this stuff. Instead, I'm going to ask you to do something. So we're going to talk about simple harmonic motion over the next few weeks, and your work is going to be evaluated by your ability to do something. I'm going to ask you to come up with something and then like carry out your own investigation. Tell me what you're going to do, how you're going to do it, make some predictions, evaluate, all that good stuff. So that is going to be the framework of what we do. It's not going to be problems on a test form that you like work through the math and give me the right answers. So as you do this work, make sure that you have that in the back of your mind, that the goal is not to like be able to use an equation. The goal is to be able to actually set things up, play around with them, and come up with information. And once we've talked about this stuff for a couple of days, I'll give you more specifics on what we're looking for. But right now, the specific set of tasks that I'm going to ask you to do rely on vocabulary that we haven't discussed yet. So we've got to get some vocabulary behind us first. So that's the first in general. The second in general has to do with how I would prefer to approach the next 3 weeks in terms of the actual grading part of what you do. So you'll be here, you'll be doing stuff, you'll be turning it in. The way that I'm going to determine your grade, unless we come to a different arrangement on an individual level, but the way I'm planning on determining your grade is to evaluate your engagement and the degree to which you are making progress toward learning new material in class. In other words, it's going to be kind of on a relative scale. And there's a couple reasons for that. The first is the work that we're doing, this is going to be the kind of the most highly mathematical stuff that we do. There's a bunch of math in here that some of you have seen and some of you haven't, and some of you have a lot of facility with and some of you don't. And so the reality is that I cannot expect everybody in here to be able to do the same level of math. When you start seeing like what these graphs look like, it's kind of crazy stuff that's well beyond what we've done so far. And I know that you all are at different levels in math. If you're in pre-calculus or calculus, you'll be good. If you're in algebra 2, there's going to be some stuff you don't understand. So I just want to make sure that what you hear is where you start and where you end is going to determine your grade. It's not that everybody has to achieve this. It's that everybody has to show that growth. I'm going to evaluate that growth based on what I see in the classroom and what you submit to me as evidence. And what that essentially means for you is if you're here and you are engaged, you will get full credit. Okay, so if you're trying your best to learn this stuff every single day, then you're going to be in great shape. If you're not here, then you should expect to need to make up that learning time somehow, whether that's coming in outside of class or doing some other work outside of class. It's not going to be like, oh, well, I was gone for 3 of the 5 days, so can I just give you what I did on these 2 days? That won't cut it. But those of you who are here, you have a path to full credit that just involves being locked into really trying to understand what you're doing, trying to learn as much as you can. And what I hope is that results in so I know a bunch of you are kind of in the same position that I and many of your other teachers are in which you're stressed out or you're burned out or both, some combination. And what I would like to do is make this class not a part of that. What I would like to do is have this class be a place where you show up, you work for 80 minutes thinking about physics, and then you could walk out the door and be done. You don't have to be stressed about it. It doesn't have to add to your burnout. And ideally, it'll be stuff that's kind of fun. It's kind of fun to play around with. We're going to look today at pendulums and Friday too, and then on next week we're going to look at springs and things like balance. It's fun stuff. And if we approach it with that evaluation framework in mind, that I'm going to be looking for your growth as it's evidenced by the work you do in class, then I think it'll be easier and more fun for all of you. If you would rather have me lay out some learning targets for you individually and say, if you can do this and this and this and this, then you'll get 60% of the points. If you can do this and this and this, you get 80. If you can do this and this and this, you get 100. I'm happy to do that with you. I want to do it individually though, because I want it to be based on your existing skill level. And so if that would make you feel better, I'm more than happy to do it. I think it'd probably be easier and more fun for at least most of you to just kind of let me evaluate it. But if you would like some benchmarks, I will provide those to you. It just means we need to talk about it individually. All right? So those are the two big things. What we're going to be talking about is this idea of something called simple harmonic motion. I'm going to go through some stuff now to kind of give you the basics, and then our work today is going to be to play around with pendulums. You're going to make pendulums, and we're going to start investigating some of the properties of objects that exhibit simple harmonic motion. So it starts with something called an oscillation, which we're all familiar with, even if you haven't used the term to describe them. Oscillations are characterized by something called a restoring force, and so we'll look at that. Simple harmonic motion is a special kind of oscillation, and while we're not going to be talking about the wave functions that are involved with simple harmonic motion, you'll see that simple harmonic motion graphically is depicted as a wave, a sine wave, all right? So when we talk about oscillations, they are generally characterized by a couple of things that conceptually are pretty easy to understand. Mathematically, they're really tricky for some reasons that we'll see eventually. The first piece is that these oscillations generally involve an equilibrium point. And equilibrium points can be really boring or really interesting. The really boring case of equilibrium is when you have a motionless object in a location where there's no net force. We call that condition being in equilibrium, we call that position an equilibrium point. If you have a motionless object in equilibrium, then it will not accelerate, which means it'll never start moving. And that's boring, but it's like part of equilibrium is the potential for no motion at all. Where things get interesting when an object is in equilibrium is when it's already moving. So you could ask, well, how does it start moving if it's in equilibrium? And the answer is, well, it's not in equilibrium when it starts moving. It starts moving, and then as it moves through a point in which there are no net forces. If an object moves through that location, then there's no net force. They will not accelerate, but they won't stop. And this is where we tend to kind of think of equilibrium, well, you're just going to stop, right, because you're at rest, but not necessarily. If you're not moving and you're in equilibrium, then you won't move. So here's an example of equilibrium right here. There are two forces acting on this gewgaw. One is upward, the tension in the string. One is downward, the force of gravity. It's motionless, there's no net force, it's not accelerating. These two forces are equal and opposite. Every time this gewgaw is in this physical location, where it is directly below my hand, it will be in equilibrium. Its acceleration will be zero. But if it's moving as it passes through that point, it doesn't just stop. Every time it's directly below my hand, it's moving at a constant velocity. And then it moves out of its equilibrium position. So we have this case where equilibrium doesn't mean put on the brakes, it means no acceleration, okay? And that means that we'll have things that are moving at a constant velocity. And if we have something called a restoring force, then we have a situation where we're going to have an object that repeatedly passes through an equilibrium position. What a restoring force is a force that tend to accelerate an object towards the equilibrium position. So what does that look like? You saw it just now with that gewgaw pendulum that I made, but there's lots of other instances where we see restoring forces. Yeah?
But with a system in equilibrium, Is the equilibrium when the object isn't moving the same as when it is moving?
Yeah, if you were to look instantaneously at that object, the net forces and acceleration are zero. What's not the same is its velocity.
Right.
Yeah, so it has a different velocity and that's it, yeah.
Right, but is that true for every system?
So I think so. It's possible that we could come up with a situation in which that's not true, but it would involve non-Newtonian physics. So we're not looking at that. All right, so if we were to have, for example, a marble on a curved ramp like this, and let's, for the time being, say we've got no friction, we've got no air resistance, we're not gonna have any loss of energy. If you were to take that marble and put it right here and then let go, then it would roll down, roll back up the other side, roll back down, roll back up the other side. We could use our work with conservation of energy to predict that every time it is up at its highest point, it's going to be at the same distance above the ground. Every time it's moving at its lowest point, it's going to have the same velocity, and the amount of energy is going to be equal. If we have this object motionless up here, all of the energy is going to be in the form of gravitational potential energy. If it's down here, all of the energy is going to be kinetic energy. On the other side, it's going to be back to gravitational potential energy. So it's this constant transformation of energy from gravitational to kinetic, back to gravitational, all right? And if we look at the forces acting on this object as it moves, there are two forces, one of which is changing direction all the time. The weight of the object, the force of gravity pulling down on it, is always straight down toward the ground, never changes direction, and never changes magnitude. There is also a normal force on this object that is perpendicular to the surface itself. That is going to change in both magnitude and direction, and there will be a net force in some places and no net force in one other place. The net force in every location except the equilibrium position is going to be in the direction of the equilibrium position. As soon as our marble is right here, gravity is pulling it straight down. The normal force is a little bit at an angle. The net force is going to be back to equilibrium. It's not going to move in that direction if it's moving away from its equilibrium position, but it will accelerate in that direction. And the farther up you go, the greater the net force becomes, and it's always going to be directed roughly toward that equilibrium position. The magnitude of the gravitational force doesn't change. The overall net force does change in both magnitude and direction. The net force is zero in the equilibrium position. So if we were to look at the net force over time, what we'd see is zero to some high value toward the equilibrium position, back down to zero, back up to some high value in the opposite direction toward the equilibrium position, but now it's on the other side of the equilibrium position, and then back down to zero. The acceleration is going to be proportional to the net force. So the greatest acceleration is at the highest point. The acceleration is zero at the lowest point. And that is going to be the opposite of the position and the velocity. So we have velocities that are going to be zero at the highest points and largest in the middle. And then we flip again for position. It's going to be at position extremes at the highest point, and it's going to be in the average position in the middle. So all of these quantities, net force, acceleration, velocity, and position, are all going up and down and back and forth, right? And we can imagine they're just going up and down and up and down and back and forth and back and forth. And this is typical of a system that's characterized by restoring forces, right? And so what we're going to be looking at is systems with predictable and linear restoring forces. When we look at oscillations, what we're effectively saying is that because of equilibrium positions and restoring forces, we end up with something that is characterized by repeated motion that reverses. So an oscillation is just repeated reversing motion. The marble on the curved ramp that we just saw is going to be an example of an oscillation. A pendulum swinging back and forth is going to be an example of an oscillation. We can think about other things as oscillations as well. this graph is showing voltage and time for somebody's heart rate. That's not a motion oscillation, that's an oscillation in electrical potential, but of course that translates to a contraction of muscles, so there is motion associated with that as well. So our heartbeat is an oscillation. And we'll see these clear patterns in the graph of the motion over time. And we can see the oscillation happening here. If we thought of this as the motion of the muscles of the heart, we would see that that's a pattern of repeated reversing motion. And there's a couple of key measurements that we need to make in order to characterize this motion. One is the period, which we give the variable capital T. That tells us how long it takes for one full cycle to occur. So the period of time between maximum voltages for a heartbeat, the period of time between being all the way up on the left or all the way up on the right or in the middle, they'll all be the same. That would be the period of motion for a marble on a curved ramp. The amount of time it takes my pendulum to start from here and end up back there, that would be the period for that pendulum. And we usually measure this in seconds, but it doesn't have to be. But typically that's what we do. And then another thing we could do, and so this is telling us how long does it take for one full cycle? Yeah?
Sorry to be the person to bring up trig, but are we talking like kind of like sine or cosine graph type of thing? Is that what you're talking about?
That's
Or
what
like,
we're gonna get, yeah.
Or
And you don't
just
have to be
one-
sorry to be the person who brought up trig, because it was gonna either be you or me. And I'd rather have it be you, quite frankly, because now everybody's a little bit irritated with you, and they're gonna be less irritated with me down the road. So that works out great for me. No, yeah, that's exactly what we're gonna see. And this is why the math gets weird, because what we're gonna be looking at is trig upon trig, right? We're gonna be looking at trig and circular motion, and we're gonna be actually using measurements of sine, and then we're gonna be approximating. It's gonna get kind of tricky, but it's also, in a low pressure situation like what I hope this is, it also ends up being kind of fun. Okay, so we can look at how long it takes for one full oscillation to occur. We call that a cycle. Or the other thing we could do is we could look at how many cycles we get every second. And so that would be, and that could be fractional, right? So it could be that you get, in 1 second, you get 2 full cycles, or it could be that you get 1.5 cycles in a second, or it could be like 0.8 cycles in a second. So however far you get in that progression from where you started back to where you started is a cycle, and we count how many of those occur in a second. And some of you are like, wait, this is how many seconds it takes for a cycle. This is how many cycles there are in a second. Isn't that the same thing? And it basically is. These two quantities are inverse of each other. So really what you need to remember is that the frequency in cycles per second of an oscillating system is equal to 1 over the period, and vice versa. The period, the units are going to be in seconds. The frequency is in a unit called hertz, which is 1 cycle per second. And you've heard of hertz before, if for no other reason than it's used for computer stuff, right? People talk about megahertz and gigahertz and stuff, and so that's like, shows up in anybody who's ever bought a laptop or a cell phone, you've seen hertz show up there before. Yeah.
Sound as well, I believe.
What's that?
Sound as well.
Yes, and that's, so, yeah, and there's tons of similarities between sound and simple harmonic motion, and we're not gonna get into that today, but think about the name, harmonic. That implies something about sound, and that's absolutely right. Sound waves are characteristics of changes in air pressure that are reflections of simple harmonic motion when we hear notes, right? Like weird noises like this, that is not necessarily like simple harmonic motion, but a beautiful, pristine note like this, well, you know, like if one were to make a really beautiful and pristine note, that would be pure simple harmonic motion of the air molecules, right? So that, yeah, that's where that comes from. All right, so let's think about simple harmonic motion here specifically, and this ties into the sound and it ties into the trig, and basically what we're saying is when we look at oscillations, if we graph the motion, we can graph position, or it turns out velocity, acceleration, or net force, any one of those things will show the same thing. We get a sine wave, okay? And the sine, this is where it gets a little weird, because it's like a sine wave does this stuff, right? It goes down and up and down and up and down and up. But if we're looking at oscillations, it's back and forth and back and forth and back and forth. So how does that work? Because the graph of position versus time has time on the x-axis. So if we were to look at the position of our marble on the curved ramp, and we were to say the right is positive, the left is negative, and we were to start it up here, then its starting position would be positive at its highest distance away from the middle. When it's in the middle, its position is 0, and it goes to the left, and its position is now the biggest left position it's going to have, and then it goes back to the middle, and then it goes back to its highest position on the right. And if we were to graph how that position changes over time, you can see it. If you watch a pendulum, you can see it's moving slowest at the extremes. It's moving fastest in the middle. So the slope of our position versus time graph is steepest at the equilibrium position and 0 at the extreme positions. That's what a sine wave is going to look like. So if we have a system in simple harmonic motion, and there's lots of them, then we'll see this sinusoidal position versus time graph, or velocity versus time, or acceleration or net force versus time. We're going to be investigating springs and pendulums. You've seen pendulums already, because I just showed you one. Springs, the kind of motion we're going to look at is this kind of motion, right? So this is also simple harmonic motion. It's not moving back and forth, it's moving up and down, but it's moving up and down in a way that would be, if we were to graph it over time, we would see it's at its highest position, and it's not moving at all. In the middle, it has its maximum velocity. At its lowest position, it's instantaneously not moving at all, and back. And then what we'll see down the road, where the math comes in, what we'll see is that the corresponding graphs of velocity and acceleration and net force are predictable based on this sine curve. In fact, you all could figure it out because we know that velocity is the slope of a position versus time graph. So here we have 0, maximum, 0, maximum, 0. You know what this is going to look like. It's going to be out of phase, but it's going to be a sine wave as well. And acceleration and net force will show that same pattern. We'll look at all that stuff later. Okay, so this I'm not going to actually play for you. It's really neat, and you're welcome to look at it. It's posted to Canvas in the module from Friday. Thank you. Let's see there. Got this person. This person. Yes. Okay, they're all good. Okay. So I'm not going to play this for you. Instead, what I want you to do is you are going to take a look at some pendulums. And there's an assignment called Predicting the Motion of a Pendulum. And what I'm going to help you with this a little bit. What I want you to start with is just make some pendulums, simple pendulums. Take something, hang it from a string, and then just swing it back and forth. And ultimately what we're going to try to play around with, and the goal by the end of the period, including extension today, is going to be to figure out how we can change it. If we have a pendulum, how do we change the period of that pendulum? How do we make a pendulum take longer to make one full cycle, or make one full cycle more quickly? And you can look it up. I mean, you're not going to ruin anything if you look it up, but we're gonna play around. I want you to actually go back and experiment with some things. Okay, so the first thing that you might want to think about is what might affect it. What are the kinds of things that you could change that might affect the period of a pendulum, and then go play around with them and see if you see any differences. And we will reconvene a couple of times to talk about this, so that we're all on the same page. And I'm gonna stop the recording and see if there's any questions before we get started.